In this section, I would like to introduce you to the multi-sensor data fusion. Multi-sensor data fusion can be defined as combine data from multiple sensors and related information from associated data sources to achieve the improved accuracy and more specific inferences that could not be achieved by using a single data source or a sensor. So basically what it says is that you might have a bunch of sensors and you will be able to extract some information or infer some information from those sensors individually. But there could be certain information that you could not infer without combining them. So you need to process them together in order to infer certain knowledge. So that process is called multi-sensor data fusion. It is important to understand the difference between sensor fusion and multi-sensor integration, because there are a lot of terminologies used in the domain. For example, sensor fusion, data fusion, information fusion, multi-sensor data fusion, and multi-sensor integration. The key differences between the fusion and then the integration are like this. As you can see from the figure, when you are integrating independent sensors, collecting data, and then feeding it to the control application directly and independently. So integration happens in the control application layer. So you can think like you are sending humidity, temperature, air pressure independently. You are not doing any processing. You collect them and send it to the application. In this case, you are sending 3 different values each time to the control application. But when you call fusion, there has to be a fusion happen. So basically, you have a temperature, humidity, and air pressure. And then in the fusion layer, it becomes a one value. It fuses together. So you can't separate it. And so it becomes a one value. And then the one single value, send it to the control application. So this is the key difference between sensor fusion and integration. The best way to think about this is think about pollution. So if you are sensing pollution like noise pollution, air pollution, and water pollution, and noise pollution, you can have these independent sensors and then write a fusion algorithm that will create let's say a level of pollution. So you have some numbers where it says, okay, if the air pollution and water pollution is above this one or in between this value, it is class A, class B pollution, class C, whatever. So you get these independent numbers and then fuse them together, and then what you are passing on to the control application is a high level class ABC. So now the data is fused together and a representative number is generated, which is the class. There are 4 stages in data fusion. We call them levels as well: signal level, pixel level, feature level, and decision level. In signal level, we are combining different signals within the sensor node itself. In pixel level fusion, we are fusing within the imaging device level itself. Fusion that happens just before the decision making is considered as feature level fusion. Fusion happen at the decision making level, we consider as decision level. Historically, these fusion stages or levels are proposed in a computer vision domain. However, these ideas and concepts are pretty much valid for IoT type sensing as well. So in high level, the signal fusion basically will try to fuse the signals together and try to create a new signal. In the pixel level fusion, what they're trying to do is basically try to highlight some of the features in the signal. So here they put the example related to computer vision, but it could be any type of signal. What they're trying to do is they highlight some part of the signal. And in the feature level, you are trying to extract features from the signal. For example, detecting anomaly from a signal. Decision level means that you have multiple algorithms that are producing end results, some decisions, and then you combine them decision together into a single decision. So that is called a decision level fusion. We can classify fusion into 3 categories based on the relationship between the data sources. So the categories are competitive fusion, complementary fusion, and cooperative fusion. So in competitive fusion, the sensors are configured to competitively and independently measure the same property. So maybe 2 different cameras, 2 different temperature sensors. So basically they are also called redundant configuration because they are measuring the same thing. So you can basically use for voting, like if there are 3 temperature sensors and 2 of them says 25, the other one says 22 or something, then 25 wins. So you can say that third sensor is malfunctioning or something. The key here is that they are measuring the same thing and the same property. In other terms, they are measuring temperature, but they are measuring temperature in the same room, same place. The other one is complementary fusion. So in this case, they are different. So they are measuring 2 different things, but they're not competing, but complementing. So they each sensor gives one perspective. So you have 2, 3 multiple perspectives to about the object. So in this case, maybe there are 2, 3 cameras watching part of the room, and then together they cover the entire room. Or it could be temperature. Each temperature might be monitoring different rooms in the house, but together they observe the same house and help to make a determination about the house. The next data fusion class is cooperative data fusion. A cooperative sensor network uses information provided by 2 independent sensors to derive information that would not be available from a single sensor. For example, if you are using 2-dimensional 2 cameras with slightly different viewpoints, and then if you are generating a 3-dimensional image by combining them and fusing them, then we call it cooperative data fusion. Cooperative data fusion is the most difficult to design, and because you have one shot about one side. So if you are trying to create a 3D image from 2 different cameras, even one error or small error in one camera could lead to inaccurate results or decrease the accuracy or reliability. So here what your objective is, like emerging view. A view try to capture something that you would not be able to capture with other sensors. In the previous one, the first one, the competitive one, what you're looking at the reliability and accuracy, because if one fails, there are backup 2 or 3 sensors, but that is competing. In the second one, you're looking for completeness because multiple sensors covering multiple areas, so you are putting them together to completely cover the whole area. But here, you are looking at the same object, same place, maybe same room from 2 different angles, and then try to create a 3D view, which is not possible by individually processing each one. Data fusion can also be classified into 5 different categories based on the input-output data types. Data in, data out, data in, feature out, feature in, feature out, data in, decision out, and feature in, decision out. First type of data fusion is data in, data out. So this is the most elementary or the lowest form of fusion that you can think of. Basically, you put the data into the fusion algorithm and it will output again the raw data. So basically here they have put example about in computer vision, you put a basic filter it to make it more reliable or accurate when we are going to use it at a later time. For example, when you say reliable and accurate in an image, if the image is too complicated, then it is very difficult to process. So you need to abstract it to highlight the basic features and then get rid of the other things that doesn't matter. So that is what we call make it more reliable. So as you can see, when you add each of these filters, they highlight certain features and then get rid of the other details, which are not very useful. We could do the same thing for any kind of data to get rid of any kind of anomalies or any other details. Because if you look at like high resolution temperature sensor, which sensing every millisecond temperature, you don't need a millisecond temperature in most of the use cases. So you need to somehow get rid of those additional or high resolution data and then bring it to a manageable part. So that is what we do here, input data and output data. This is the second type of data fusion, data in and feature out. We also call feature extraction or shape extraction. So basically you input the data and then it will extract important features out of that. So basically, if you take the same example of image, you will input a basic pixel value and then output will be like features of connected labels and components. So you can see in this illustration, they come up with some kind of feature extraction within the image. So now it is no longer resulting any raw data, but now it is features coming out. This is the third type of data fusion where we input features and take output features. So the algorithm produces a new output feature based on the input features. So best way to explain is using an example. So let's say you have an ultrasonic sensor that you can measure the depth or the distance. And then you have a camera sensor which can be measure the shape. So basically both use very signals and then do the processing of the signals, which is raw data, and create the feature with like what is the distance or the depth, and then the camera also capture the pixels and convert it into a shape. So both has features and features, and then it input into a data fusion algorithm, and it will create the volumetric size of the target, because you have the depth, you have the shape, now we have the volume. So volume also a feature. So two sensors did the sensing, had the raw inputs, converted to features, independent features, and then independent features are fed into the sensor fusion algorithm, and the sensor fusion algorithm generated another feature which is called volume. Feature in, decision out is the fourth type of data fusion. This is the most common data fusion. Basically, the state-of-the-art machine learning algorithms always do that. They take features as input and then they generate outputs. For example, if you want to recognize an object or classify object, let's say a human versus horse, There could be features that are unique to humans, like 2 legs versus 4 legs. Horses have a tail, and then they have a different size. So all these unique features of horse and human get into the algorithm of the machine learning algorithm, and then once the features are decided and extracted from the images, it can decide whether it is a horse or a human, which is the decision. Decision in, decision out is the last or the fifth step of the data fusion hierarchy. Basically, the data fusion algorithm takes decisions as input and generates output. For example, pattern recognition could be example where individual decisions are made on what is the activity performed in a particular point of time, and then you put them together to identify what is a pattern. What did the person do in a household? So each of the sensor would individually tell you one part of the scenario. For example, a pressure sensor embedded in the bed might say that person got up at particular time, so you infer that. So that is a decision, individual decision. And then someone switch on the smart plug on the kettle. So that is a infer that a decision that human has is now in kitchen. So likewise, each individual sensor or bunch of sensors get together and make a decision. So these decisions are combined together to identify what kind of pattern this person is following in that particular day. So in that case, you can identify any anomalies of that pattern and other behavioral analysis tasks. So the important is that the algorithm is taking decisions generated by individual other sensors and again output as a decision, like whether this is a normal behavior or abnormal behavior. Again, it is a decision. When we talk about sensor fusion, the most common sensor that come to mind is the accelerometer, gyroscope, and the magnetometer. They are very useful sensors that can be combined together to understand the 3D orientation in humans or any objects. So that is why the mobile phones are using these sensors to determine variety of activities and behaviors we are performing at a given point of time. As you can see from the illustrations, pitch, yaw, and roll are the 3 dimensions of movements when an object can perform when they are moved through a medium. Identifying these orientations are quite important to understand the context where the object sits in. Over the next 3 slides, I would like to talk about this particular use case where they have developed a sensor fusion algorithm for 3D orientation detection by combining 3 different sensors: gyroscope, accelerometer, and compass, or the magnetometer. You can find the details about their use case in this research paper, but the main steps and summary is as follows. So their sampling rate is 8.96 samples per second. The gyroscope resolution is 16-bit and the sensitivity is 0.007, and they have used accelerometer with a sensitivity of 0.00024. What you can see from this figure is the raw data that they have acquired while the sensor is stationary on the desk. As you can see, the measurements are in different scales, therefore they are not useful to be used in a fusion algorithm. so they need to be calibrated or bring them into the same scale. Here it is 0 to 200, 0 to 2, 0 to 50. So these need to be bring into one single scale, 0 to 1 and 1 minus. So if you look at the accelerometer, the XY axis are approximately 0, which is correct. And then Z is minus 1. X and Y are 0 because there's no acceleration, because we said that it is on the table. And the only acceleration present is the Earth's gravity, which is denoted by the Z-axis. And that is why denoted by the minus 1. And with regards to the gyroscope data, the hardware is stationary, as we told you before. There's no rotational movements applied to the system. Therefore, all the fluctuations are just white noise. So this white noise is inseparable from the gyroscope data. So this diagram summarizes their fusion algorithm or the fusion system. You can look into the details and the different equations they use to do these calculations, which I'm not going to discuss here. But what they have done is they have used the calibrated accelerometer signal is to obtain the roll and the pitch. And roll and the pitch are noisy calculations, and the algorithm combines them with the gyroscope signal through a Kalman filter to acquire a clean and not drifting roll and pitch angles. So basically a Kalman filter is a filter that helps to reduce the noise of any type of signal. Then they have implemented a tilt compensation unit which uses a magnetometer signal in combination with roll and pitch to calculate the Young rotation. So what I want to show you here is that these sensors can be not much use if they're taken independently, but when they're fusing together, you can complement the results, make the results more accurate, and generate new insight that were not possible to generate independently. So this is a very simple example and very widely used and very useful example where the data fusion brings value to IoT applications. The fusion algorithms we discussed earlier are quite useful to track objects and their movements, especially in the IoT context, from ranging from a mobile phone to any other object. Typically, you don't need to read continuously. You can read at intervals to save the battery. Sometimes manufacturers add dedicated processors to process these sensors if they are consuming a lot of energy in the traditional processor, because then the processor is occupied by these processing tasks of the sensors, which you don't want to. So you have a secondary processor to do the processing related to the sensors. Let me now summarize the advantages of using multiple sensors. If we have multiple sensors, then it helps us to deal with failures of sensors, because there are redundancy and it leads to more resilience and robustness. Multiple sensors can also reduce the uncertainty and give more confidence, because now we know that one sensor is not randomly saying something. Because there are multiple sensors saying the same thing, we are more confident. And if you have multiple sensors that capture multiple dimensions, then it helps us to sense and get a more comprehensive description about the given environment. It also helped to enhance the collective information content obtained by multiple low power, low precision sensors. Previously, we talked about that having two different sensors like depth and the shape, and then create the volume. So these are enhanced value by capturing information from low-cost sensors. Data fusion also enables to hide any critical data sources or semantics, because if you remember when you talk about data fusion and data integration, in the data integration we are sending raw data to the application separately, independently. So the application can see exact raw data. But if you are doing the data fusion, then by the time it goes to the application doesn't know exactly the raw data. So if you are looking at very sensitive like military applications or medical applications where you don't want the application to see exact raw data, because potentially they may be get hacked. If it is a cloud storage, it could get hacked, or it could get leaked, or unnecessary processing could happen. But if you do the data fusion at the earliest point, maybe within the sensor node, then the rest of the data flow has no idea what is the data source or the semantics. So that could be a more security or a privacy benefit. Finally, multiple sensors also help to improve the resolution, because you can get more data points now about a given object or environment. There are significant challenges in using multiple sensors. First one is imperfection. For example, sometimes sensor data could be uncertain or inaccurate. The second one is ambiguity. Some data could be missing and some data could be outliers. Third one is conflict. For example, same sensor type reports different data from the same location. For example, temperature sensor, two temperature sensors saying two different things about the same location. If there are more than two, probably you can go for the majority. But if there are only two sensors, then it would be challenging, because you don't know which one is the wrong one. So there's a conflict. The next challenge is the alignment. Previously, I talked about the importance of having sensor data annotated to space and time, because when you're analyzing the data, the space and time is very important, because you need to align them together. So all the data related to a particular location, when they are processing, you need to know at what point the data points are collected. For example, if you are looking at a time frame like 10 a.m., you want to combine the data collected at 10 a.m. from all the sensors in that particular location. But if you don't capture time, or if you cannot align data coming from different data streams to a one timeline, then it is going to be challenging to analyze them. Trivial features could also reduce the accuracy. So what does this mean is that there are a lot of data streams in an IoT application. So for when we are talking about each sensor, you need to extract features from each of them. But these features has to be representative. If you extracted very simple features which are not very distinct, it will make it difficult for the machine learning algorithms and data fusion algorithms to make a proper determination. Therefore, feature engineering is really important. For example, if you are using accelerometer data to determine whether someone is running and walking, you really need to pick the features that helps you to classify them. If you pick some very trivial features, then it will be difficult for the machine learning algorithm to actually classify the activity. Finally, the heterogeneity. The heterogeneity could be different formats like analog, digital, textual, audio, video, or heterogeneity could be like different units, different frequencies, different sampling rates, different systems, so on. So these are only a subset of challenges, or the main challenges that you need to deal with when you're fusing multiple sensors together.